Srapa, you were absent yesterday. Why?
Sir, actually there was power cut in our area and my mobile
Huh?
network was not working. Sir, there was
What?
power cut. I was having network issues.
Oh,
Sir, there was power cut and my mobile data was also not working.
if something happens during exam, what you will do? And that is why this time exam will be offline.
Yes, sir.
And all future class test also will be offline. Not
Yes,
only
sir.
teaching will be offline, even class test also will be offline. अभी कितने लोग 7 लोग आए लेट मी सी Okay. I think you should start now because, yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So somebody is missing. I don't know who is missing. And okay, we should start. So I will start with something different but something highly mathematical. I will go slow. The visibility may be poor, so I will request you I will enlarge it and then yes, go line by line. So today we will have a discussion on orthogonality of mode shapes. What does it mean? And we will also prove mathematically that mode shapes are orthogonal. But first we should understand the definition. What do we mean when we say mode shapes are orthogonal? This is not ordinary orthogonality of vectors, because here when we say mode shapes are orthogonal, we say this is that mode shapes are orthogonal with respect to mass matrix. Mode shapes are orthogonal with respect to stiffness matrix. So you first write down these two sentences. You first write down these two lines. Let me explain these two lines and then we'll go back to the proof. So today you have to write down line by line because visibility may not be very good. I will enlarge it. Chalo. So you write down this line first and then next line. So this is R. This is R actually, subscript R. This is S. So first you write down these two lines. This is the definition of Morse orthogonality. This is slightly different from our usual orthogonality where we multiply the vectors directly. But here we are multiplying the vector first with mass matrix in between and in the second line with K matrix in between. So first line says motsepts are orthogonal with respect to mass matrix. Second line says motsepts are orthogonal with respect to stiffness matrix. Let me repeat again. First line, you only write down these two lines, nothing else. You write down these two lines. So the top line where mass matrix is there, it means motsepts are orthogonal with respect to mass matrix. Second line says motsepts are orthogonal with respect to stiffness matrix. Now, when you look at these two lines, be careful. R and S, they have to be different. R and S, they have to be different. So a question may come. What will happen if R is equal to S? Obviously, if R is equal to S, right side will not be 0. Right side will not be 0 if R is equal to S. So orthogonality principle is valid for different motsepts. R not equal to S. What will happen when R is equal to S? We'll discuss that. But this is a powerful property. First, we will prove it mathematically and then we will see what is the use of this property. So let me go back. How do we prove it? So let me begin with this line. Do you agree with this line? First of all, K into Rth motsep is equal to omega R square into mass matrix into Rth motsep. Do you agree?
Yes, sir.
ये कहाँ से आया?
From equation of motion.
But from in equation of motion, I never said it is Rth motsep. It was plane X. Remember? It was plane X. There was no subscript R. There was no subscript for omega. So now can I write it? Of course, we can write it. Why? Because omega R and Rth motsep, they are solution. They are one of the solution pair. Omega R and XR, they are one of the solution pair. There will be n number of solution pairs. This is one of the solution pair. So for each solution pair, left hand side will be equal to right hand side. But if omega R and XR, they do not belong to solution pair, then left hand side will not be equal to right hand side. So left hand side will be equal to right hand side for each solution pair. What do I mean by each solution pair? Omega 1, X1, omega 2, X2, omega 3, X3. So like that, for each solution pair, left hand side will be equal to right hand side. So this is our beginning, where R can be any motsep and corresponding eigenvalue is omega r square, or corresponding natural frequency is omega r. So let us start with this line. You write down this line and then pre-multiply left hand side and right hand side by, don't write this line now, don't write this line. Pre-multiply left hand side and right hand side by transpose of Sth mod set. So now you come to third, this line. So what, don't write line number 2, don't write line number 2 now. From line number 1 or equation number 1, you come to equation number 3. So what we are doing in equation number 3, left hand side we are pre-multiplying transpose of Sth mod set. Right hand side also we are pre-multiplying transpose of Sth mod set. So we get this, and then we take the transpose both side. नहीं ठीक है तो, so once you agree this, then you go back to line number 2. Okay, now let us go back to line number 2. So left hand side will be equal to right hand side for another solution pair S. So this will not only be equal for Rh solution pair, this will also be equal for Sh solution pair. Actually, this will be left hand side will be equal to right hand side for any of the solution pair. So this is another solution pair. This may be first mode, this may be second mode or third mode. So this is another solution pair. So write down equation number 3, and here you pre-multiply transpose of Rh mode set. Write down equation number 2 and then pre-multiply transpose of Rh mode set. Pre-multiply transpose of Rh mode set. First you write down equation number 2 and then you pre-multiply transpose of Rh mode set. फिर हमें क्या मिलेगा? We will get this. Yeah, we will get this line. Line number 4. So now we have 4 equations. Okay, 1, 2, 3, 4. We have 4 equations. Then what I am saying? Take the transpose of equation number 3. What is equation number 3? Let me go back. This is equation number 3. Transpose of left hand side, transpose of right hand side. Transpose of left hand side क्या होगा? This will come first. You know that AB transpose is B transpose A transpose. So transpose of left hand side will be XR transpose K transpose, and transpose of transpose is T will go out, and because K is a symmetric matrix, K transpose will be K itself. So we get this. So equation number 3, if we take transpose of the everything on the left hand side and transpose of everything on the right hand side, we get equation number 5. I will stop here for 2-3 minutes. Try to digest it. Mathematically, is it acceptable or not? ठीक से देखो और बोलो कि ओके. So now we will focus on equation number 4 and equation number 5. But how we got equation number 4 or line number 4 and line number 5? You see each derivation. Are you convinced? Because we have used little bit of vector algebra. Let me tell you, AB transpose is B transpose A transpose. So when we take transpose of a product, transpose of the last component comes first. So now if we agree that this is okay and this is okay, what I do is I subtract line number 4 from line number 5. क्या मिलेगा?
So I have a doubt in equation
बोलो
5.
बोलो 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 हाँ.
So since we took the transpose, on the left hand side there is K matrix. So how do we know K matrix is symmetrical? Because like we are writing K transpose as K.
No. How do we know? Na? This is a property we have seen that in multi-degree of freedom system that we have modeled, not only in this problem, in all the I think that we have discussed in the very first class. Mass matrix is diagonal. K matrix is not diagonal, but K matrix is symmetric. So this we can utilize as long as K matrix is symmetric.
Yes, sir.
And for all lumped parameter model, let me make it clear. For all lumped parameter model, that is this discrete modeling, K matrix will always be symmetric.
Okay, sir. Thank you.
But there is another K matrix may come from another consistent modeling. There it may not be symmetric. But for lumped parameter modeling, matrix will be always symmetric. And that is needed. If that is not there, I cannot replace K transpose by K matrix. Okay? Now what I do is I am subtracting equation number 4 from equation number 5. फिर मुझे A line मिलेगा. Agree? And that gives me mode orthogonality equation. So subtracting 4 from 5, I get this. Now because omega r cannot be omega s, r is not equal to s, I am saying r is one solution pair, s is another solution pair. So omega r cannot be equal to omega s. So this bracketed term cannot be 0. So the remaining product, he has to be 0. So this is first derivation. And if this is put into this one back, if this is put into this equation back, then this is 0. This also comes out to be 0. So finally, we get both the mode orthogonality equation. So both the equations are proved here. But you go through it, you study it. You study it because we will spend some time. It's not that easy. You study it, how we derived it. So both the mode orthogonality equations, when I'm saying both means one is with respect to mass matrix, other one is with respect to stiffness matrix. So both the mode shapes are, mode shapes are always going to be orthogonal with respect to mass matrix as well as K matrix. Now you go back to the problem that we have solved. I think mode shapes, पहला mode shape कितना था? I don't remember. 1, 2, 1. Second mode shape 1, 0, minus 1. We have not solved second mode shape. I am telling you, second mode shape 1, 0, minus 1. And third mode shape we have solved in the last class 1, minus 1, 1. So now you check with both mass matrix and K matrix. Are we getting orthogonality principle satisfied? You have to take different combination of R and S value. 1 with 2, 1 with 3, 2 with 3. चेक करके बताओ in the problem that we have solved. Mode step number 1, 1 2 1. Mode step 2, 1 0 minus 1. Mode step 3, 1 minus 1 1. So these three mode steps, are they satisfying mode orthogonality principle or not? Check करो एक बार. All the three cases. क्या क्या three case है? Mode step 1 with mode step 2, mode step 1 with mode step 3, mode step 2 with mode step 3. तीनों चेक करके देखो. Mode step orthogonality principle is getting satisfied or not. Are you getting it? Nandana,
Yes, sir.
are you getting it?
Yes, sir.
Okay, so I presume that you will get it. So now the question is, what is the use of it? So you write down another thing. Suppose I remove mass matrix, I remove K matrix, I multiply Rth mode step directly with Sh mode step. Is it also becoming 0?
Yes, sir.
No, all the three cases. So this is a home task. This is a homework that mode steps. So far, what we have proved? We have proved that mode steps are orthogonal with respect to mass matrix. Mode steps are orthogonal with respect to stiffness matrix. Now your homework is so that they are directly orthogonal. From using these two, using this orthogonality, using mass matrix orthogonality and stiffness matrix orthogonality, we can prove that they are directly orthogonal. Okay, we can prove that. And if I have, so how many vectors I have? I have n number of vectors. If the degree of freedom is 3, how many mode steps I will have? 3. If the degree of freedom is 10, how many mode steps I will have? 10 mode steps. And all the 10 mode steps are orthogonal to each other. Okay. And if I have n number of vectors which are orthogonal to each other, what I can do? Go back to your second semester mathematics, what we can do? Any idea? I have 3-dimensional vectors which are orthogonal to each other. Okay, I have mode shape 1, mode shape 2, and mode shape 3. And somehow these three mode shapes are orthogonal to each other. Then what I can do? What I can do? See, what is the advantage of collecting n number of orthogonal vectors? What is the advantage? At least you have done mathematics. Okay, you don't know. I'll come to that. I'll come to that in 5 minutes. Tab tak socho. But before we come back again to orthogonality, let us see what will happen if R and S, they are not different. So if I multiply two vectors which are identical, obviously right hand side will not be 0. Right hand side will be a non-zero quantity. We call it generalized mass of rth mode. कट गया यहाँ पे generalized mass of rth mode, MR. Similarly, in K matrix, if I multiply transpose of rth mode shape with rth mode shape itself, so because R is same as this R, right hand side will not be 0, it will be a finite quantity, non-zero quantity, we call it K subscript R, generalized stiffness of rth mode. And then this generalized mass and generalized stiffness, they are related to each other with rth natural frequency. So rth natural frequency is square root of kr by mr. So if I can find out kr, if I can find out mr, I can directly find out rth natural frequency. So in the mid-semester examination, there was a question where I had given second mode shape and you were supposed to find out second natural frequency. This method can be applied. However, in mid-sem, I didn't teach it. So I was expecting another method. This is one method. There exists another method. And you can also find out rth natural frequency if you know rth mode shape. Now listen to this question. It is interesting. I have K matrix and mass matrix. If in addition I give you rth natural frequency, we can find out rth mode shape. Converse, if I give you rth mode shape, you can find out rth natural frequency. So study how it can be done. Let me repeat the discussion again. K matrix is given, M matrix is given. If one of the solution pair is known, then the other solution parameter can also be obtained. Matlab, if rth natural frequency is known, then with very simple mathematics, I can find out rth mode shape. Converse, if rth mode shape is known, I can find out rth natural frequency. How? You study yourself. I think this is answer to the second question. If rth mode shape is known to me, I find out kr, I find out mr, and then using this I find out rth natural frequency. Okay, so with this, let me again go back to this question that mode shapes are orthogonal. How do I use it? So we will go to next PPT. I'll bring next PPT in just 2 minutes. I think right now you can't see anything. I'm changing the PPT, so you just wait. Can you read it now? A new PPT has come now. Expansion theorem. इसको लिखो, पूरा लिखो. Expansion theorem, I mean, this is a fundamental of vector algebra, that in n-dimensional space, I have n number of orthogonal vectors. Then any other vector can be represented by a linear combination of these orthogonal vectors. And then these orthogonal vectors are called basis vectors. These orthogonal vectors are called basis vectors. So this is a very beautiful property of the set of orthogonal vectors. So if I have in n-dimensional space n number of mutually orthogonal vectors, then any other vector can be expressed as a linear combination, that is C1 into x1 plus C2 into x2 and Cn into xn. This is an arbitrary vector in that space, n-dimensional space. So there can be infinite number of arbitrary vectors, but each of them can be expressed by this linear combination. C1, C2, they will be different for different vectors. So if I jump from one arbitrary vector to another arbitrary vector, C1 बदल जाएंगे, C2 बदल जाएंगे, लेकिन this linear combination will be able to get back this value. So in brief, we write summation r is equal to 1 to n CR XR. This is expansion principle or expansion theorem. This is a beautiful property, and we will use it again and again in many cases. Anybody having any question with this expansion theorem?
No, sir.
Expansion theorem needs that the vectors x1, x2, x3, they have to be orthogonal vectors. And if you know, or I don't know if anybody has told you, in n-dimensional space, there can be many set of orthogonal vectors. So mode shape 1, mode shape 2, mode shape 3, they give me one of those sets. It doesn't mean that these are the only orthogonal vectors. No. There can be another set of orthogonal vectors. And this linear combination will be valid for the second set also. Fine. But in vibration, we are only interested in mode shapes as the orthogonal set of vectors. But there can be another set. No, there can be a third set. There can be a fourth set. But we are not interested in them in vibration. In vibration, we are only interested in the set of mode shapes or mode shape vectors. Mode shape number 1, mode shape number 2, mode shape number 3. So whenever we write x is equal to linear combination of Cx XR, then this is Rth mode shape. Okay? Now, this CR, a value depend करेगा on the arbitrary vector x, and we can calculate it by this formula. इसको prove करो. Can you prove it? This formula tells us how to calculate each coefficient for a given arbitrary vector. For a given arbitrary vector, I can find out each coefficient by this formula. But can you derive the formula? थोड़ा try करके देखो. I थोड़ा ट्राई करके देखो न्यूमरेटर यू ट्राई टू इवैल्यूएट द न्यूमरेटर क्या मिलेगा इन द न्यूमरेटर x की जगह ए वाला लिखो फिर हमें क्या मिलेगा today onwards you have to use all your knowledge in mathematics. You only evaluate the numerator जहां पे x is equal to a वाला लिखो पूरा एक्सप्रेशन लिखो फिर क्या मिलेगा फिर कैरी आउट each multiplication. ভাবলে আমার 45টা ফেটে গেছে পুরো তুলো বেরিয়ে যাচ্ছে किसी को मिला आर यू एबल टू गेट इट किसने बोला यस सर
सर नितेश
नहीं बट देर आर 11 स्टूडेंट्स बाकी लोगों को क्यों नहीं मिल रहा you have to apply mode orthogonality principle with respect to mass matrix. See, now I will go very fast. This small mathematical things I will not explain. I will not explain. I will believe you know the basic mathematics. Okay, still I will give 2 more minutes to other students. अंडर ग्रेजुएट में किसी यूजी स्टूडेंट्स किसी को मिला दिस
Yes, sir.
फॉर्मूला किसने बोला
Yes, sir.
Sir.
हाँ ओके नाउ डू यू थिंक we can replace mass matrix by K matrix. The formula still remains same. Try करके देखो. Suppose I replace mass matrix by K matrix. Do you think the formula still holds good?
Yes, sir.
Then why I am using mass matrix and not K matrix here?
It is very simple with mass
Correct,
matrix.
correct. Mass matrix is diagonal, so this mathematics will be simpler. However, the formula is valid even if I replace mass matrix by K matrix. Okay. This is very interesting. I will tell you other property. So, given an arbitrary vector x, first we can arrange it as a linear combination of the mode shapes. That is number one. And I can also find out the coefficients C1, C2, etc. by this formula. Fine. Now, how to calculate C1, C2? So, थोड़ा you can easily do it. But before that, चलो, हमारा problem में x1, x2, x3 क्या था? You remember? In our given problem, what was x1, what was x2, what was x3?
Yes, sir.
You know. Now suppose I have an arbitrary vector 1, 2, 3. C1, C2, C3 कितना होगा निकालो. Now I give you an arbitrary vector 1, 2, 3. So use the formula and find out C1, C2, C3.
So
हाँ.
C1 is 4 by 3, C2 is -1, and C3 is 2.
C3 is
2.
2. Okay. बाकी लोग, see, this speed is also important. If you think for every question I will wait for 1 hour, that cannot happen. Speed is also important. C1, C2, C3 maximum 5 minutes, not more than that.
Yes, sir.
कितना है C1, C2, C3?
1.33 -1, 2 by 3.
2 by 3. Okay. So if any arbitrary vector is given, we can always find out C1, C2, C3. A C1, C2, C3 क्या है? Actually, they are the contribution of each mode set into the arbitrary vector. So every vector in the nth dimensional space, it consists of contribution coming from each mode set. How much contribution? It is represented by the coefficients C1, C2, C3. Okay? So we'll come back to this concept next class, that contribution C1, C2, C3. But today we discussed how we can find out the value of C1, C2, C3. And then I will conclude today's class with a new concept. What is meant by normalization of mode shape? What is meant by normalization of mode shape? See, we have already seen that. What is the problem with a mode shape? Can anybody tell me? What is the problem with a mode shape?
So we can't directly find calculate it.
No, but we can get the mode shape through matrix iteration method or whatever may be. But see, a solution pair consists of two parameters or two values. One of them is eigenvalue or natural frequency. The second one is mode shape. For a given mode, natural frequency will be unique, but mode shape is never unique. Let us go back. What was our mode shape? 1, 2, 1. First mode shape. Can I say that 2, 4, 2 also first mode shape? I mean, if I put x is equal to 2, 4, 2 and not 1, 2, 1, will left hand side satisfy right hand side?
Yes.
Answer is yes. So this is something interesting. Mode shapes are not unique. If some vector is first mode shape, any scalar multiple will also claim to be first mode shape. Any scalar multiple. 2 into 1 to 1, 3 into 1 to 1, 4 into 1 to 1, and then I can get infinite number of first mode shape. So this is a problem with mode shape, that mode shapes are not unique. So when mode shapes are not unique, how do we write them? So the method of writing a mode shape by a standard method is called normalization. So normalization is to write a mode shape in a particular manner. There are infinite way I can write first mode shape, but no, I will not go infinite way. I will go by a particular method. So there are two normalization method. One is standard normalization method. Standard normalization method says मोड से वेक्टर में जो भी मिला उसको पहला कोएफिशिएंट से डिवाइड करो. That means make the first member equal to 1. So suppose I say 242 is my first mode shape. Then divide each member by the first member, that is 2. हमें क्या मिलेगा? 1, 2, 1. So if take any arbitrary mode shape and divide each value by the top value, whatever remains, that is called normalized mode shape number 1. Now what is the beauty of this normalization? That for any arbitrary mode shape, my normalized mode shape will be unique. Normalized mode shape will be unique. It will always come back to 1 to 1. It will always come back to 1 to 1. So this method of normalization is called standard normalization method. In vibration, we don't use it. We use it, but there is another normalization which is called mass normalization method. In mass normalization method, what we do? We create from an arbitrary vector, we create another vector phi dividing 1 by square root of mr. So first we calculate mr by this formula. And then from an arbitrary mode set R, we create this vector, and this is called mass normalized vector, and he is unique. And we can prove that for mass normalized vector, this product will always be 1. This product will always be 1, and the second product will always be omega r square. So just look at this 4 line, you write down them, because today I am not going to give you the PPT. You write down these 4 lines and see if they are correct or not. This is known as mass normalized mode shape. Phi is called mass normalized mode shape. So how do we get the mass normalized mode shape? We start with any expression for Rth mode shape. We calculate generalized mass for Rth mode shape and then divide 1 by square root of mr with Rth mode shape. Whatever we get, we call it mass normalized mode shape. This will be unique. This will be unique. And property of mass normalized mode shape is that for mass matrix in between, this product will be 1. For stiffness matrix in between, this product will be omega r square. Check it. Is it coming? So today I stop here. Little bit of mathematics is there. You go through this mathematics again and again. Next class will be next Tuesday. So you are getting a good gap, a gap of almost 6 days. But that will be in classroom. Next Tuesday class will be in VNIT classroom. And we will start application of this. ठीक है? आज इतना ही. कुछ पूछना है किसी को? In between, I will send you the mid-semester solution and marks. I will send. Maybe after Holi, I will send that. आज यहीं पे खत्म करते. Okay? I'm closing it today. We'll meet next Tuesday. You can leave. You can.